Hello, in this video we are going to see how we can design a printed monopole UWB antenna and simulate that in CST. So here this is the structure for that monopole, and the radiating element is circular in shape and the ground plane is partial, and this is the response that we are getting. Here you can see that it has an ultra wideband response. So the one of the main important characteristics of this antenna is it has the partial ground plane. So this partial ground plane is the main reason for getting the UWB application. So let's see how we can do that. So before going to that, I would like to show you this thing, because previously we have designed a circular patch antenna with an inset feed like this thing. So we have that simulation in our channel. In that case, we had the full ground plane. Because of this full ground plane structure, we were getting very directional beam pattern like this. Here you can see that the radiation which is going onto the back side, that is the back lobe, is very less, and it has a very directional pattern because of the full ground plane. And because of this ground plane structure, it is having a high Q. That means that the response, it has a very narrow band response, because at the resonance there will be uh, the reflection from the ground plane will be forcing all the radiation into the front lobe, and because of this ground plane reflection, it is causing high Q, because all the energy is stored inside the dielectric, and it is causing the narrow band performance. This is one of the main characteristics of this circular patch antenna that we have considered. So we are going to use the same radiating element structure and are going to analyze how this partial ground plane is going to give us the ultra wideband performance. So how we can extend this bandwidth to the ultra wideband. So let's see that. In this case, we are going to feed that patch at the end. So here we were not able to say it is a circular patch antenna, because we are going to have a partial ground plane, and we are going to say this is a printed monopole antenna, because here you can see that this is the radiating element which is backed by the partial ground plane. So this is a printed monopole antenna. This structure is acting as the monopole. So it is not like a circular patch antenna, but it is a printed monopole antenna. So if you have to design a UWB antenna, you can use different structures instead of circular patch. Like you can use the uh, like rectangles, or any spear like structures like this thing, or anything can be replaced this circular patch. So we can use any radiating elements, and it will be called as monopole antenna. So if you search on the Google, you can see different types of printed monopole antenna with replacing this circular patch with different shapes. And one of the main characteristics that we have to consider here is it will be having a partial ground plane. So the ground plane is not full, it is partial. So it will be approximately covering these feed. So this is the main characteristic, and when you consider here, you can see that the radiation pattern is like omnidirectional pattern. So here you can see that in this plane it is covering the entire region, and in this plane it is null. So it is an omnidirectional pattern. And if you consider here, you can see that how the S parameter is varying. So here you can see that the S parameter has good performance from 2 to more than 12 gigahertz. So it is giving us an ultra wideband response. So let's see why this partial ground plane is giving us this ultra wideband response using the simulation. So let's go for the simulation. So this is the dimension of the structure that I am going to consider. So here the main parameter is the radius of the patch. So what I am preferring is I would like to have the first resonance at 2.4 gigahertz. So that's why I'm going to select the radius of the antenna based on that. So I'm going to select, I'm using this calculator and using the resonance frequency 2.4 and epsilon r 4.3 and FR4 substrate 1.6 mm. So I'm going to use FR4 substrate. Sorry, I didn't mention that. And based on that, the physical radius is A, that is 17.1. That is what I'm going to use it here. A is 17.1 mm and next one is 3.1 mm feed width. So to calculate that feed width, I am using the Pasternak microstrip calculator and substituting all these things. You can see that when feed width is 3.1, you will be getting an impedance of 50. So I'm going to use that also here. And you can use different values for the feed length. Here I have taken around lambda by 4 here, and this is the dimension of the ground plane. So you can optimize the dimension of the ground plane to have the ultra wideband performance. So here I have taken little bit more than this feed line. So my aim is to cover up to the feed line. So this is how I have taken the ground plane. So let's design that in CST and see that. So let's do that. Click on new template, and this is an antenna, which is a planar antenna. You can select the time domain and the frequency. I'm going to take 1 to 12. Okay, and finish. So first of all, I'll be designing that circular patch having the radius 17.1. So let's go for that. So this is the patch. Okay, so outer radius is A. A is 17.1, x under y is under 0. So it is on the top of the dielectric. So I have taken the dielectric thickness as H, and we have to take FR4. Okay, FR4 lossy. Then, okay, so A is 17.1 and it is 1.6. So now we have the patch ready here. Oh, sorry, this is not FR4. Sorry, my mistake. We have to take this as PC. Really sorry. So we have to take it as PC. Then our aim is to use that feed line. So for that you can use the brick. So this is the feed and this is the feed width. So I'm going to take FW as the parameter to design this feed width, and it has to be from here to some length, right? 14.75. So I'm going to give it as from minus A. So it is from minus A to minus A minus feed length. So this is also PC. Oh, sorry, here I have to give the thickness. I missed this thing. So here y minimum is from minus A to minus A minus FL. So let's preview that. Feed width we have taken as 3.1 and feed length we have taken as 14.75. Okay, so we have that also. So we have the radiating elements. Okay, my next aim is to means sum up both these things. So it's like it's not touching, so maybe I will edit this feed dimension to include minus A plus 1 so that it will be inside that, so that I can add it easily. This is just for adding purpose. So to add, what you have to is you can select the patch and you can use the boolean and add and then click on the feed. So it will be adding both the structures. So now our next aim is to design the dielectric. So I'm going to take, so in all the direction along the x direction I'm going to take 10 mm on both sides. So it is minus A minus 10, and on the other it is A plus 10, and y minimum it has to be up to this point. so that is minus A minus FL, and Y maximum, here I'm going to take an offset of 5. So this is the dielectric, it has a thickness of 8, and this is the F of 4. So let's preview that. Okay, then click OK. So we have the dielectric. Next is we have to draw the ground. So the ground is also on the same dimension, minus A minus 10 and A plus 10, and along the Y it is minus A minus FL and A plus 5. It is on the ground plane, so 0. The material is PEC. So here you can preview and then click OK. So we have the antenna now. Okay, so I'm going to okay. So our next step is, as we have designed the radiating structure. Oh, sorry. Here we have to use the partial ground plane. My mistake. So what you can do is, maybe I will delete it and draw it again. So now we have to draw the ground plane. Really sorry for the mistake, and its dimension is the partial. So along the x-axis it is the same, that is minus A minus 10 to A plus 10, but here it is from this position, that is minus A minus FL to, that is from this point to 15 mm. So minus A minus FL plus 15. So let's see that. So 0 0. Okay, so now the partial ground plane is ready. So click OK. So to see where the ground plane is actually situated below the field line, I'm going to edit material properties just to give some transparency to the dielectric so that I can see. I'm going to give the color green. So we will be able to, so if you click on this components, you can see that where the ground plane is actually situated. So now we have the monopole, printed monopole with the partial ground plane. So my next aim is to assign the port. So for that you can use the usual step. Click on F, it will select the phase. When you double click, it will select that phase, and you can go to VBA macros, solver, ports, calculate port extension coefficient. As it is the microstrip, these values are already selected based on our selected phase. You can either calculate it and draw it by yourself or construct port from the big phase. So then it will be constructing a port. Whether it is created, where is the port? Okay, so we have the port now. So the port is created. Now our main step is to enhance the accuracy. One thing you can do is you can increase the mesh settings here. So if you increase the mesh setting, you will be getting more accurate result, and once it is set, you can start the simulation. So let's do that. The simulation is complete. We can see the S parameter here. You can see that the wideband response which is obtained due to that partial ground plane. Here you can see how the response is obtained from around 2 to more than 12 gigahertz. So let's put the field monitors. Where is this? So we have to check the electric field, surface current, and far field. Okay, so maybe transient broadband we can give for all the frequencies, and then we can use the electric field. So for that, as we have to select only for the structure, I'm going to use the structure bounding box, and I have to take the frequencies 2.4. Oh, sorry, why it is not coming? 2.4 and maybe uh, 5, 7. So I'm going to take the electric field at different frequencies to see how we are obtaining this wideband performance. So next maybe surface current apply, then 7, then what are the frequencies? 5 and 2.4. Okay. So we have all the things. Next again start the simulation. We can check after the simulation. Okay, the simulation is complete. Let's check the far field now. Okay, so maybe we can select the frequencies where the resonance is occurring. So here you can see that how we are obtaining that omnidirectional pattern. So you can show the structure and transparency for field transparency. So here you can see how we are obtaining the omnidirectional pattern. So in case of that full ground plane, we were obtaining the directional pattern like this, right? You can see that below the ground plane there is no radiation. Here you can see that because of this partial ground plane we are getting omnidirectional pattern. And let's see the surface current. Okay. Oh. Sorry, my CST crashed, so I have to resimulate everything again. So these are the field monitors I set because I forgot what I set earlier. So these are the field monitors. So now the simulation is complete. So let's see the surface current distribution. Okay, so for that I'm going to select mainly the patch. Okay. So we can select the patch now, and you can see how the electric field distribution is happening inside the patch. So first I am going to select the lower frequency 2.4 gigahertz, and you can observe carefully how the field distribution is changing with increase in the frequency. Maybe I will drag this to get more clear indication. Okay. So this is at the lower frequency. So when you animate the field, you can see that the entire patch, so inside the patch also are getting excited, right? So if you increase the frequency, you can see that more than the center, the sides of the circular paths are getting excited. So if I increase the frequency again, you can see that the excitation at the center is almost null and the excitation is happening at the ends. So the current is mainly getting excited at the ends. And we have to take the ground plane also, the partial ground plane also. Here you can see that how the ground plane is also excited. So maybe before that I will show you the ground plane on ground plane excitation for the full ground plane in the circular patch antenna simulation. So you can take the surface current. So this is the okay. So first of all I will take the patch alone. Okay, so this is the patch alone. So here you can see that how the excitation is happening on the patch. So now I'm going to select the ground plane. So this is the current distribution on the ground plane. Here you can see that on the ground plane, wherever the patch comes, the surface field excitation is happening only that place. There is no much excitation on other ground plane areas, right? So there is no excitation here, but only below the patch there is an excitation. But in the case of these half ground plane structure, here you can see that there is an excitation happening on these ground planes. So there is a coupling between these patches and the ground plane, and there is a capacitance happening because of this patch and the ground plane. So this parasitic capacitance also giving rise to some excitation. So here you can see that at lower frequencies, the main excitation is on the entire patch and the ground plane is also providing some excitation. Here also you can see that at higher frequencies, you can see that the end of the patch is, that is the end of the circular patch is giving more excitation than at the center. And here also you can see that this ground plane is also contributing for the excitation. Because of all these contributions, we are getting a wider response. So this 2.4 gigahertz response is mainly due to this patch excitation, and at higher frequencies we are getting the responses from the end of the patch. So here you can see that how the patch is getting excited, and that is why we are getting very wide response, very wide response as parameter. Okay, so this is the wideband response that we are getting. So these are some of the parametric optimization I did earlier to study how the surface wave excitation is happening. So this is based on our parameter. So here you can see how the partial ground plane is giving us these type of response. Okay, so we can see what is giving us wideband response when we are using a partial ground plane. So when we are using a partial ground plane, it is like we are getting impedance matching over a wide range. That means that if we are using a full ground plane, we will be having high Q factor because there is a reflection from the ground plane happening below the circular patch, and it is giving rise to very high Q factor and very narrow band response. So when you remove the part of the ground plane, it will lower the Q factor because the energy storage inside the dielectric will be less, and it will give rise to wider impedance matching. And this also we have observed at low frequencies, the entire structure, the patch and ground is acting as the radiator, but at high frequencies we have seen that the current concentrates on the end of the patches, and which is giving rise to the wideband response. And we also can see that the current is not only on below the patches, but it is also distributed on these partial ground planes. This is also giving rise to the wideband response. That's why we are getting ultra wideband response when we are using a partial ground plane. That is how we are designing a printed monopole antenna for the ultra wideband response. I hope you get some idea about it. Thank you.